So in the previous lecture, we have talked about the most of the volume is near the equator. That means we have discussed this theorem, which tells you that if you have a unit ball in the d-dimensional space, and if this is your north pole, if I fix the north pole with x-axis, x1 axis, then most of the volume is in between these two lines, and this line is actually denoted as, that is x1, or I can say a plane, it is x upon c, sorry, x1 is equal to c upon d minus 1. So all the things is in between these two, that is x1 is equal to minus c by square root of d minus 1. In between this, that we have discussed in the previous lecture. One immediate implication of this analysis is that if we draw a 2-point at the random from the unit ball, so if we can pick up any 2 points here into the random ball, sorry, into the unit ball, with the high probability that their two vectors will be nearly orthogonal to each other. So what I'm saying is, if you pick up any 2 points into the d-dimensional unit ball, and you pick any 2 points into that unit ball, and then these 2 points, or I can say that these two vectors, if this is the origin, then these two vectors are nearly orthogonal vectors. Orthogonal means they have angle between them, it is 90 degree. So that two vectors are perpendicular. Specifically from our previous to previous analysis, where we have conduct the things that the geometry of high dimensional space, we have seen that the most of the volume is near the surface. We have talked about this. The most of the volume is near the surface. So all the volume is in that. In that we have discussed that with the high probability both will have the length of 1 minus big O of 1 by d. And from the previous lecture analysis says that if we define a vector in the direction of the first point as a north pole, there is a high probability that the second projection of order 1 by square root of d, that you can see from here, it is approx the c upon square root of d minus 1, I can say it is less than or equal to 1 upon square root of d, and that's why it is of d of 1 upon square root of d in this direction. And this implies that there is a high probability that the angle between these two vectors will be pi by 2 plus or minus big O of 1 by square root of d. So in particular, we have this following theorem. We will not discuss the proof of this theorem, but let us see what is this theorem is says. Consider drawing of n points. When I say it is a point, but it is, they are not points, they are the vectors. So I'll just denote it by x1 bar, x2 bar, up to xn bar at random from the unit ball. This is the d-dimensional unit ball. Okay. So from the d dimension, unit ball, with the probability one minus big O of 1 by And then we have this, the first one, that is mode of xi is greater than 1 minus 2 ln of n upon d. If this is xi bar. For all I, this is true. The second one, that is a dot product between, that is xi dot xj is less than or equal to square root of 6 into ln of n upon under root of d minus 1 for all I is not equal to j. So what is this means? That the dot product of these two vector is tends to 0 as d tends to infinity, that you can see from here. And what does it mean of this? It says that if d tends to infinity, then this will be tends to 0. So the a modulus of any vector is bigger than 1. So this will be the theorem which says that if you pick randomly any 2 points into the random ball, then there is a high probability that two vectors are orthogonal. So ultimately what we are saying is in d-dimensional unit ball, every point is nearly orthogonal between them. Now one might be confused with the fact that can be nearly all points of the unit ball are very close to surface at the same time. What we have discussed in the previous lecture is, as I told you, that a volume is near the surface. At the same time, I'm also telling that a volume is near the equator. Okay, so at the same time, nearly all points are of the boxes they are near the equator. And the answer is to remember the points of the surface are satisfying the equation, that is x1 square plus x2 square up to xd square is equal to 1. So for each coordinates here, typically the value that we have, it is plus or minus b co of 1 by square root of d, you can say. And in fact, this is often helpful to thinking of picking a random points of the sphere is very similar to picking a random point from this vector. Now, the next task that we are doing is the generating points uniformly at random from a unit ball. So now how to generate a uniformly points into the unit ball. For example, consider generating a point uniformly at the random ball on the surface of the unit ball. For example, if we are in two-dimensional space, if you want to generate a point from the circumference of the unit radius, that means if you have given a circle and I can ask you a question that can you generate a uniform random points from this circumference of the circle, unit circle. How to generate? Can somebody tell me? In 2 dimension, we have to generate a random point. They are uniformly distributed. What to do? So first idea is to construct. So there is a two coordinates is needed. So x coordinates and y coordinate. X coordinate is varies from -1 to 1 because this is a unit circle. So that is, this is the 0 point, and this one is 1 0 point. If you can fix your x axis and y axis here. This is your 0 -1 point. Sorry, -1 0 point. This is 1 0 point, and this one is 0 1 point, and this one is 0 -1 point. So if you pick your x, which is independent, generate a coordinate uniformly, random from the interval -1 to 1. So it is easy to establish a uniformly distributed number between -1 and 1. That we can easily do. Similarly, if I can generate y also using uniformly distributed using means in the interval -1 to 1, then what will happen? This produces these points, but distributed over the square, because the x is -1 to 1 is this one, and y is between -1 and 1 is this one. So it will be generate a points in this inside the square is a large enough to complete the certain points in the unit sphere. The project of each point onto the circle, unit circle, the distribution is not uniform since more points fall on the line from the origin to the vertex of the square and then fall on the line from the origin to the midpoint of the edge of the square due to the difference in the length. So if you can generate the points here and the points here, what will happen? Suppose it may happen that the points are some points are falls here and some points maybe fall here, but this points, those who are falling outside the circle, will not be considered. So we need to discard all the points which are outside the unit circle and project the remaining points into the circle. So whatever the remaining points which are there, that is, we need to work out with that. Another way is to generating a random points inside this unit circle using the polar coordinates. So if you can consider this is x is equal to r cos theta and y is equal to r sin theta, then here there are two parameters x and y, x and theta. So you fix your value of r. Suppose you want to generate a points inside the circle, then your value of r should be less than 1. So you can generate your points r is between 0 and 1, uniformly distributed. You generate a points of r which is between 0 and 1, and you can generate a theta which is from 0 to 2 pi. So it will have full circle. So that will generate, and the another way is to generate the points uniformly distributed using this polar coordinates. That is easy to do that. Now when you do this is the procedure in the higher dimension, this method does not work. What we have discussed just now, that dropping out all the points which are outside the square, it is not work. Since the fraction of the points fall inside the ball drop to 0. So whatever the points if you generate, most of the points are outside the circle, and a ratio that you can consider, those who are coming inside the circle, is nearly 0. So the method which we are discussing, that is generating x in the interval -1 to 1, y is in the interval -1 to 1, and then you can just club them out, x square plus y square. If you can club them out as x square plus y square, then whatever the value which are less than 1, you can keep them. All other value you can discard. Okay, but this method will not work for the generating points on d-dimensional unit board. So the solution is to generate the point whose coordinates is an independent Gaussian variable. So to generate that one, we need each and every coordinates of is independent Gaussian variable. So there are in d-dimensional unit ball, there is x1, x2 up to xd. There are this many variables are there, and each and every variable should be independent Gaussian variable. Gaussian means they are distributed normally. Generate x1, x2 up to xd using the mean 0 and unit variance. Namely, what is the unit variance? Gaussian is 1 by square root of 2 pi e power minus x square by 2 with unit variance and mean 0 on the real line. Thus, the probability density function that you can have, so the probability density function here of x bar is p of x is equal to 1 upon 2 pi power d by 2 e power minus x1 square plus x2 square up to so on xd square upon 2, and it is spherically symmetric. Normalize this vector x bar is x1 x2 up to xd. Normalize means you have to divide by its norm to the unit vector. For example, if I can say you what is the x bar is, here we have given x1 x2 up to xd, then what, how to normalize it? That's divide by its norm. Norm means mode of x bar. Mode of x bar is square root of x1 square plus x2 square up to xd square. So you will have it is x1 upon mode x1 x, x2 upon mode x bar up to so on xd upon mode x bar. So this is a normal vector, and this falls inside the unit ball. It is a unit vector, namely it is x bar upon mode of x bar. It gives the distribution that uniform over the surface of the sphere, and in this way if you generate a random numbers, then it will be uniformly over the surface of the sphere. And we should note here, then once the vector is normalized, the coordinates are no longer statistically independent. So this variables that we have considered here, they are not statistically independent variable. Okay. Another way is to generate using the polar coordinates, as I already told you, that generate a point y bar uniformly over the unit ball and scale the point by x upon x bar. Generate a surface by scalar. So what we are doing to generate a point y bar uniformly over the unit ball, that means surface and interior. So I want a y bar to be generated uniformly over the entire unit ball, surface as well as inside. First, what you have to do, scale the point x upon mode of x bar upon mode of x bar. Generate on the surface by scalar rho belongs to 0 and 1. What should be the distribution of gamma be with a function of r? It is certainly not uniform. This gamma is not uniform even in the two dimension. Indeed, the density of gamma at r is proportional to r for d is equal to 2, and for d is equal to, it is proportional to r square. So in the by similar reasoning, so what we are saying is gamma density, whatever the gamma, it is a proportional to r, and in two dimension. In three dimension, it is proportional to r square. So in the similar reasoning, we give the density of gamma at the distance r is proportional to r power d minus 1 in d-dimensional space. Solving now what is the density? That is integration from r is running from 0 to 1 c into r raised to d minus 1 dr is equal to 1. This is a density function, and if you integrate this will be d r power d upon d. Limit is from 0 to 1 equal to 1. We'll need to calculate what is the value of c from this. So that will gives me c by d minus 0 is equal to 1. So that will gives me c is equal to d. And another way is to see the formally the volume of the radius r. Unit means r ball in the d-dimensional space is r is to d into vd. The density at the radius r is exactly the d by dr of this. So I say that it is d into r raised to d minus 1 into vd. So what is this? It is the density of the volume of the radius r ball is equal to this in d-dimensional space. So this is a density, the volume. This is the volume, and the density is the below. Density at radius r is equal to d by dx of this. Sorry, d by dr of d power r power d vd You have this. So we have to pick this rho r with the density is equal to d r power d minus 1 for r over 0 to 1. And we succeed by generating a point y bar is equal to rho into x bar upon mode of x bar, uniformly at random from the unit ball using the convenient spherical Gaussian distribution. And we'll need to see what is the Gaussian in high dimension. So for that we have, so can somebody tell me what will be the Gaussian in one dimension? Normal distribution in one dimension. Here we are talking in Gaussian in higher dimension, but before that you should know what is a Gaussian in one dimension. I'm asking you what is the distribution function or density function in normal distribution, PDF. It is easy, difficult.
1/√2 pi sigma exponential raised to -1 summation xi minus nu upon sigma square. 2 sigma square.
Okay. This is the normal distribution in one dimensional case. What will happen in d-dimensional space? So the d-dimensional spherical Gaussian with zero mean and variance sigma square in each coordinate has density function that is p of x. So this is the density function in d-dimensional unit ball. Instead of this √2 pi, here it is 2 pi power d by 2. Instead of sigma, we have sigma power d, e power x minus mu. But this is, instead of x, it is mode. So it is exponential power minus of mode of x bar square upon 2 sigma square. Okay, so this 1 by 2 is outside, not inside. So this is the variance, sorry, this is the density function for normal distribution or a Gaussian distribution. The value of the density is maximum at the origin. So this density function is maximum at the origin, but there is very little volume is there. At origin is very little volume is there. When this variance is 1, the interesting probability density over the unit ball center at origin. Yet most of zero mass since the volume of such ball is negligible. In fact, one needs to increase the radius of the ball nearly by square root of d before that significant volume, and hence the significant probability mass. If one increase the radius beyond square root of d, the integral barely increase even through the volume increase, since the probability density dropped off much higher rate, and therefore we have very interesting result is known as Gaussian Annulus theorem. It says that most of the theory, means formally it is saying that nearly all the probability is concentrated in the thin annulus of order big O of 1 at radius root pi. So what does it mean of annulus? Anyone know? Anyone know what is the meaning of annulus geometrically? We're not discussing the proof of this, but let's see what is the theorem says. So anyone know what is annulus? Annulus is nothing but suppose in two dimensional if I talk. If you have a two circle, concentric circles, that means their center is the same. So this is one circle, another one is this. It's not look like circle, but you can assume that it is a circle. Okay. Both circle have the same radius. This in between portion that we got, it is known as annulus. So what is this saying? That this theorem is saying that the nearly all the probability is concentrated in the thin annulus of which big O of 1 at radius root d. So this distance that we have a root d, that is a radius, and this one is big O of 1. So everything is concentrated in between this, in between two circles. That it says, this theorem says. Let us see what is the theorem stated. For d-dimensional space, spherical Gaussian with unit variance in each direction for any beta which is less than or equal to square root of d, all but at most 3 e power minus c raised to beta square of the probability has mass lies within annulus square root of d minus beta less than or equal to mod of x bar less than or equal to square root of d plus beta, where c is a fixed constant, fixed positive constant. So what is this? Actually, this will represent the this strip. This is mode of that means center is 0, 0, 0 in d-dimensional space. And the radius is square root of d plus or minus beta. Beta is also constant, which is less than or equal to square root of d. So this theorem is says that for d-dimensional spherical Gaussian, almost all mass is lies within this annulus. We will not discussing the proof of this, but the theorem is there. You need to understand that. Now the next concept, it is a random projection. So first of all, you should know what you mean by projection. And it is very useful to reducing the dimension. Okay, so if you want to reduce the dimension, then the random projection is very useful. So can somebody give me some idea regarding the projection?
Can you consider scatter diagram as a random projection?
Scatter diagram is a random projection. Yeah, one sense. Yeah, you can say that. See, actually the projection is something you project. For example, when you're shooting a video, we are shooting into 3 dimension. We are shooting, or we are when we are taking a photograph, we are taking that photograph in the 3 dimension. But that photographs we'll see into 2 dimension. Is it so? That is a projection. So it is actually reducing the dimension. For example, if you have here one line, and what will be the projection of this line onto this line? So if this line is project on this line, then it will have just one point. But if this line is on this way, then it is a line segment of this. So what I'm saying is, you just suppose you just say that here it is one light. If I throw, if we throw one light from this, whatever the shadow is appear on this line, that is a projection. Here, if this is a line, straight line, that is I'm taking a vertical line, and if I throw a light from this side, then the projection of whole this line is just become one point. So that is actual meaning of a projection, and it is very frequently and used subroutine in the task involving the higher dimension data. Nearly what will happen in the near neighbor search. Okay, in nearest neighbor, a search where given the data of the endpoint in the where n in RD space, where generally n and d are very large, and the database can process, pre-process and stored in the insufficient data structure, and it will take a lots of time. And thereafter there is a query of point in RD, and R2 we need to find out the approximate nearest database point of that query point. So instead of finding the original one, we need to find out what will be the approximate nearest database is there. And since the number of queries is often very large, because n is large, d is large, it will take a query time, a time to answer a single query. should be a very small. Ideally, the small function of log n and log d. So when we have a query, that query time should be very small so that we can process our data very fast. And that is should be a polynomial in the function log n and log d. For this and another problem, the dimension reduction. So dimension reduction where one of the project that database point of k dimensional space where k is very small than d. Usually depends on log d. This k usually depends on log d. So that much reduction will be there and can be very useful for as long as relative distance between the points of approximately preserved. And whatever the situation is happening in D, that means, for example, if I have projected this line onto this line, then the distance between these two lines, that is the projection we have here, whatever the projection we got here, is the same as a distance between these two lines, or some slightly modification is there, but it is preserved. Preservation of the nature will be there, and that will be useful to constructing or predicting something from the higher data or database is there. So first of all, you should know what is the exact definition of the projection. So it is a function. Okay, so the projection is a function. Projection f from Rd to Rk. That we will examine, in fact, many related projection into the following manner. Let us pick. What we'll do is we'll pick k vectors, that is u1, u bar, u2 bar up to uk bar independently from the Gaussian distribution. So we have to pick up this k number of points from the Gaussian distribution, that is 1 upon 2 pi raised to d by 2. So your mean is 1 and variance, sorry, mean is 0 and variance is 1. Mode of x bar square by 2 minus. Now for any vector v, so this u1, u2 up to vk, they all of them are belongs to Rd. You have to pick up k vector from Rd, and we define now for any v bar, it is in Rd, we define the function f, that is a projection function. F of v bar is equal to a dot product of u1 bar into v bar, u2 bar into v bar, u3 bar into v bar, up to so on uk bar. In this into is a dot product between these two vectors u1 and v bar, and the projection of this is a function. And can you say that this function f is a linear function? See, to see this one, let us see one example. Okay, For example, I have a R3 to R2. So as per this k vector you have to choose u bar, u2, uk. So here we have R2. So let us choose two vectors. Any two vector you can pick up, no problem. Right now we have forgot that whether they are in Gaussian independent, linear independent or not. We'll forget that. But let us pick two vectors in R3, two vectors. So I was just picking 1, -1, another one is -1, 1. So this is my u1 bar and this is my u2 bar. Now I want to define a function of v bar. V bar means f of x bar, or I say x bar is x1, x2. So what is f of x bar? As per this definition, it is u1 into v bar. u1 is this, that is 1 -1 dot product with x1, x2, -1, 1 dot product with x1, x2. So what will be this gives? This will gives me x1 minus x2, and this function will give, or this dot product will give me minus x1 plus x2. So this is my function. I can say it is a projection from R3 to R2. So this is just giving you an example. So can you prove that this f is a linear function, or I can say linear transformation? Linear transformation you already discussed in your linear algebra course. So can somebody recall what will be the definition of a linear transformation? Yes, anyone?
Moving from one vector space to another.
Yeah, moving from one vector to another vector space, then it satisfies certain property. What are that properties? Then we can say that is f is a linear map.
Addition and multiplicative.
One person, please.
Vector addition and scalar multiplication.
So vector addition, it preserves the vector addition and the scalar multiplication. So that means v1 plus v2 is equal to f of v1 plus f of v2, and f of alpha v1 is equal to alpha times f of v1. For every v1, v2, this is true, and alpha belongs to a field, whatever the field it is defined over this f and w. So this is a known as linear transformation. It's called linear if it satisfies these two conditions. So my objective, or I can give you as a task, that prove that this projection map is a linear map. Can you prove that very easily? Why it is true? Because u1 bar plus u2 bar dot product with v bar will gives me u1 bar dot v bar plus u2 bar dot v bar. This is true. Okay, because this dot and this addition is a it's distributive property. Now using this, what we are going to discuss is f of v bar is equivalently square root of k into v bar. What does it mean? Whatever the distance you found in this RD space, so this f, you have f, which is a map from RD to RK, where D is very large, K is very, very, very small. So this is a notation for K and D. So compared to D, the K is very small. And what we are doing, this is a projection map. Projection map is already defined here. It's look like this. And what we are trying to prove here, or we'll discuss that V of x bar, the mode of this one, is equivalent to K into square root of K into mode of V bar. What does it mean? Is that if you pick any two vector here, because of this situation, f of v1 bar minus v2 bar, as this f is a linear map, we can write down it as v1 bar minus f of v2 bar. So due to this, if I take the modulus here, the modulus of this one will give, and using this, what we can say is a distance will be preserved, or it is a proportional to a distance in RD. It is a proportional, or I can say it is equivalent to a distance in RK. So it is just a factor. Square root of K is multiplied. For example, I give you that example. Suppose this is a line and this is another line. If I project this line onto this one, so I want to project this slanted line onto this line, then this position of this light is there depends on that the distance. So any 2 points, if I pick up here, the distance between them will be scalar multiple of some scalar multiple will be there, is a distance between here on this line. So that is known as a random projection theorem, which tells you that the distance will be preserved, and that we can discuss in the next lecture because it is already 11. Fine. If you have any questions, you can ask.